Okay, so it's 9 p.m. in Japan time. Let me get started. Hello, this is Junichiro Horikawa, and this is the 34th episode for Houdini Algorithmic Live. This is the weekly Houdini tutorial live stream that I'm doing, and this is the 34th times. And the topic that I chose for this week is to create a procedural walking robot using a new feature from Houdini 18.5 called KineFX. And here's a sample that I have made using it. So I'm not really, I myself not a animator or rigger or anything, or related to gamings or anything. I'm mostly working in architectural field, so I don't really need to do this kind of things. But I thought, I found it really interesting. I mean, creating something like this procedurally using like the new features called KineFX which can be controlled, which can control the skeletons, create the skeletons, and control in a sub level. So this is one of the trial that I did, creating this kind of procedural robotics. And the good thing about this that you can control it in sub level is that you can relate with other kind of sub level procedural changes, like changing the number of legs and like these, and update this so that I can quickly change this robot to a multi legs having more than 6 and so on. So I guess this is pretty interesting. Yeah, and while the process that I'm going to show you today might not be a logical stuff, because I have done it. I have found this process doing and by trying and errors, so might not be a best way to do what I wanted to do to create this kind of things, but just think that this is kind of one of the idea how you can achieve this kind of effect or procedural animations, right? So let me get started. So to do this, you need to have a Houdini 18.5 because I'm using the specific node which is available from that version. So remember that, which is the KineFX. Okay, so I'm gonna start by creating geometry node. Then what I always do is to first create a null node to store all the parameters which I want to control later on. Currently I don't have any parameters that I could use, I could think of, so I'm gonna leave it blank for now. Now let's try to create a profile for the robot that I want to create, and I want to create something like a disc-like robot. So I'm gonna start by creating a circle. Then for this one, this will going to be the base of the robot, base of the legs and shapes, the bodies. So I'm gonna place the orientation to ZX and change this to polygon. Now I think I can use this division parameter to control the number of legs. So each point, each vertices of this polygon could be a position for the legs. So maybe I could parameterize this value, division. So going into the controller, I'm going to create an integer parameter. Let's name this leg num, say from 3 to 12. Okay, and let's copy this parameter to a division parameter for the polygon. Okay, I'm gonna leave it at 6 for now and see if I can change this later on. Okay, next thing, I would like to create a base skeleton curves out of this polygon shape. So what I'm going to do is to use could be just done using anything, but just going to use a primitive wrangle. Okay, so primitive wrangle. And since this, I want to use this base polygon as the base of the body, I'm going to lift this up a little bit to upward to Y direction to make it as a root of the body. So let's go back to the polygon and maybe raise up this polygon by 1 to Y direction. Okay, and probably I might also want to change this radius for the polygon, so let's also add some parameters for that. Give a float value. Name this radius from 0 to say 1. Okay, and I'm gonna keep it as 0.5 for now. Copy this, paste it right here to the uniform scale. Now connect this to a primitive wrangle. I'm gonna name this as base skeleton. Okay, now first thing I would like to do is to create a leg for which goes from the center of this polygon to each of the vertices, and then create a vertical line which is going to stand on the ground, which is the XZ plane in this case. So let's do that. To do that, I'm first going to retrieve all the points from the polygon. So PTS goes to prim points. I mean, the same thing that I'm going to write here can be done using detail wrangle, but I'm just gonna do it using primitive. Okay, and so let's try to create the center point first, which is not really necessary, but let's do that. Okay, so int, I'm gonna name the name of the center point send pt, and add the point at the center, which is at p, and let's just raise up a little bit upward so that I can later on use that point to place a body geometry. Okay, something like this, and let's see if the point has been created right here. Yeah, you can see this. Now next thing I would like to do is to connect this center point with each of the vertices, and then go to a floor to create a leg-like lines. Okay, so before doing that, I'm going to set the name for this point that I have just created for the center point, and later on I'm going to use that name attribute in order to define which point will be used as a controller for the inverse kinematics for the KineFX. Okay, so string, or I'll just say set point attrib name for this point, send pt to be root. Okay, now if I look at the geometry spreadsheet, let's check to the point attribute, and I do have a point right here, named as root. Okay, right, now let's create a leg for each vertices on the polygon, so I can create a loop through all the points that I have retrieved here, like this. First create a for loop, then retrieve the points retrieve the point number from each point array. Okay, let me just save this on as a desktop so that I don't lose the process. I'm just gonna name this robot. Okay, now let's retrieve the position for that point, for each point on a primitive. Let's name this pos. So the attribute that I want to look for is the capital P, which is the position of the point at PT. Okay, now let's create a new point at this point. I mean, I already have those points right here, so maybe I still can use that point. Maybe I don't really need to add new point. Let's set point attrib 0 name to tpt t. Since this is going to be the top point, I'm going to use t as the preface of the name. Then for each point, I'm gonna add I after this t. Okay, oops. I didn't have a TPT, so it should be PT. Okay, now let's check. So for each point that I have right here is named as T0 till T5. Okay. Now let's create a primitive as a polygon, polyline, so that I can create a polyline connected from the root to each point. So int prim equal to add prim as polyline, and for initial curves I can add this root, which is a sempt, together with those points on the vertices, which is this pt. So pt. Alright, now I need to add additional curves, which is going to be used as a leg, and for that leg I need at least 3 points, one on the top, one on the middle, and one on the tip. Okay, in order to create a inverse kinematic. Right, so let's do that. Let's calculate the position for the middle point. Okay, so I'm gonna name that mpos, which is in between the position right here and the ground positions right here. So say that could be a current positions right here is this one. So this could be positions multiplied by no. I'll just copy the position itself, then I can I think I would also want to move this point to outward a little bit so that I can have this kind of shape for each leg. So to do that I can retrieve the center point of the primitive, which can be retrieved as at p. So, and this is the current point position for each vertices, so I can add position plus a position minus at p, which is going to be the direction vector going from the center to each vertices, and let's multiply this by some parameter value like offset. Okay, let's say around 0.4 for now. Then currently the height of that point is around here at the same height of this primitive, but I want to change this to the middle point, middle positions from this point to the ground, so I can just change the y value, multiply by 5, multiply by 0.5, make it the middle point positions. Okay, now I can create a new point at that point. I'm gonna name the point name as MPT and use at point at mpos. Okay, now the new point has been created. What I want to do with this one is to add this point on a primitive that I've created right here using add vertex, like this, so that I need a 0 first. Okay, now looks good. Now I just need one more point to complete the leg geometry. Alright, so let's do that. So the last point that I need is the bottom point, but before going to that, I also want to name this middle point with the name attribute like I did for the top part and the root. So I'm gonna copy this part and name this middle point, which is MPT, as M plus I2AI, so that each middle point has a M as a preface. Alright. And later on I will use these M and T's for filtering which point that I want to get. Okay, now let's go to the bottom point. Now to do that, I'm first going to create a position called vpos and copy it from the position for each vertex. Now what I just need to do is to just change the y position to 0. Okay, pretty simple. Now let's add it as a new point. bpt is equal to add point 0 vpos. Right, and add vertex to add this point in a primitive bpt. Alright, looks good. Now same for other points. I'm gonna name this with b preface so that I can use it for filtering later on for inverse kinematic. Okay, I think that looks good. Now I don't really need those polygon anymore, so right after I have created all those necessary curves, I can just say remove prim num and say goodbye to the polygon. Bye. Okay, right. Now this will going to be the base of the geometry of the skeleton that we're going to use in order to create a procedural animations. Okay, now let me just check the point attribute. Okay, I think I'm having some points which has no attribute, which is because I needed to name this bpt. Okay. Okay, now it seems fine. Right, now so let's convert this curve into a skeleton using a new node from a KineFX set from Houdini 18.5, which is, in this case, what I'm going to use is a node called skeleton, which you can convert the curve into a skeleton, which will add a lot of parameter or a lot of attributes related to a rig, which I don't much know what those each attributes do. I just know what I want to do for this specific purpose that I want to create for this tutorial, but for other than that, I don't really know what could be what those attributes could be used. I just need to explore this later on. Okay. Now next I would like to create a inverse kinematic basis, so let's do that. To do that, I need another information, which is to define which point is going to be used as a tip point for the inverse kinematic, and which is going to be the middle, which is going to be the root. Okay, so in this case, this will be the tip point, this will be the middle point, and this will be the root point for each legs, for each inverse kinematic for each legs. Okay, so to do that, I saw in the Houdini side effects document, I was looking for that, how I can create that by looking at the documentation page on a side effects. It seems like there are some ways to do that, and the way that it was showing is to first use the delete joints to delete unnecessary points in order to just keep only the points that I need for the guide. In this case, for this point and this point for each legs, so I can just delete this point on the center, which is named as a root. Okay, so using delete joints, I can specifically delete this point by setting a filter saying name is equal to root. Now it seems like it's same as doing a delete node, but this is specifically for the joint, so I guess I need to it might be better to use this one instead of using delete. I'm not really sure, honestly. But the documentation says that's the way to do it, so I'm just following that way. Okay, so next I would like to apply some information to the middle point for some later purposes. When you want to bend each legs, you always want to have this bending going outward like this. You don't want to bend the legs like inward like this. So to do that, you need to have some kind of additional informations. Which way should this middle point be bended toward? So that's the information that I'm going to add now as an attribute. Okay, so I'm going to use that point wrangle and only access to the middle point by saying the name is equal to m asterisk, so that I can only, the point wrangle will run only on to a attribute name is equal to m with any value. Okay, so any value with any name value, any name attribute with starting with m will be used with this code. Okay, so currently I'm looking at each middle point using this code. So, and what I want to get is the middle point of the tip point, the end point, which construct this curve. So this point and this point, and the middle point will be around here. And I want to get the directional vectors from this middle point to this current point position, so that this direction will be the guide direction vector. Which way should this curve be bended toward? Right, so let's do that. And the easiest way that I could think of, I mean, obviously it might not be the easiest, but first I'm going to retrieve the neighbor point position, the neighbor point numbers using neighbors from this point, so that I can retrieve this one and this point for each legs. Okay, so like this. So this should give you 2 points this point and this point as a array. Now let's also create a average positions, set it as 0, 0, 0 for now, and I need 2 point positions from this neighbors, and I think I know how many numbers are there in this neighbors because there's just going to be 2. So I'm going to specifically retrieve the first point neighbors and the second point neighbors like this, and also get the position 1 and position 2 from each of the point. Okay, like this. Now calculate the average positions by adding those point position together and multiply by 0.5, which will give you a point somewhere around here. Okay, if you want to check it, you can add the point to check where those positions that I have created. Okay, it looks correct. Now what I want to really make is the directional vectors going from this point to this point. So instead of adding the point, I'm going to create a directional vector which is going from this point to the original point, and you can do that by subtracting the current point position by the point that I have just made, the position that I have just made. Now let's also normalize this to keep the length of this direction as 1, because I just want to use this as a guide, and then I'm gonna apply this as an attribute to this middle point, named as their direction, and later on I'm gonna use this. Okay, let's check this. So there's a direction attribute right here, and only the point with the minimum with the M preface, which is these ones, should have those direction value applied. Okay, looks good. Now let's name this IK infos. Right, now, oops. Let's also add some groups to every points that I have retrieved using a delete joints. I'm just going to use a group node to determine that these are the IK target in inverse kinematic target. So let's name this. Let's just name this IK target and set it as point. Okay. Now I am going to merge those two stuffs. One is the skeleton and one is the IK target. And the reason why I'm going to merge these two is because later I'm going to use the solver to calculate, do the animation procedure animations inside this to do some iterative animations. Then after this I'm going to calculate the inverse kinematic using a node called IK chains. Now I'm going to I'm just gonna keep solver empty for now and going in directly into IK chains to show you how this one works, how this IK inverse kinematic works. Okay, and currently I have 6 legs, so I need to create 6 IKs, inverse kinematics chains, right? So to do that, what I'm going to do is to used a for each loop to have maximum 6 iterations, or based on the number that I have set right here, the number of legs. Okay, so let's say for each number, and I'm going to copy this value right here, and then, or maybe I can just say for each primitive, maybe. Well, I'll just keep it as this. Okay, and I want to make it a feedback loop so that after one calculations, I can go to the next one to do and do another calculations for other legs, and keep the previous updates, previous IK chains updates. Okay, so that's the reason. Now let me also change this to a fetch feedback. Okay, now there is two types. There's going to be two types of geometry retrieved from this one. That is because I have merged these two different types of geometry, which one of is the skeleton, one is the IK target. So first thing I would like to do is to split those into two, and I'm going to use IK target group to split. So from the first input, will be able to retrieve the IK guide, IK target information, and from the second input, I'll be able to get the base skeleton. Okay, and what I'm going to do is to update the base skeleton with this for each loop, and inside the for each loop, I'm going to apply this IK chain right here. And for the second input, I'm going to connect this IK target as a inverse kinematic drive parameter. Now, okay, now next, what I'm going to do now is to create a IK chains by clicking this plus button, and which will create a one inverse kinematic options right here. And for each leg, I think I need to enter this detail, informations right here, the name of the root, name of the middle point, name of the tip name. Okay, and that is equal to the name of that I have entered for each point, which is this one, this one, this one. Okay, so for the root name, which is this point, the name starts from T, so I can just say T, and the middle name starts from M, and the tip point starts from B. Now for the later values, I need to specify the numbers for each point. And if I look at the point attributes, there is a number from 0 to 5 if the total number of the legs is 6, equal to 6. So I kind of need to access to those numbers in order to use it with this one. And actually, I'm using a for, that's kind of a reason why I'm using for each loop, and I can kind of retrieve that information, the value from 0 to 5 from this for each count detail attribute. If I look at the detail attribute of this for each count, you see that there's a attribute called iterations, and this iterations will be counted up, incremented from 0 by 1 at each loop iterations. So starting from 0 and goes up by 1, so 0, 1, 2, 3, 4 to 5. So I can directly use this value for the name appended with these T, M, and B. Okay, so what I just need to do is to use an expression to access to the detail attribute at for each count. The attribute that I want to access is iteration at 0 position. Okay, well, unfortunately it doesn't show you the result, but hopefully this is correct. Now I'm going to copy this one, paste it right here. I need this back quote. Do the same for this one. Okay, I'm also going to check this match name because both the skeleton and this guide for IK is using the same name for the point. Okay, so both skeleton, this one, have a name from MB to T, and this one also has MB to T, and the position is the name is going to be used to match those 2 points together to define the actual position after the IK. Okay, so that's how it works. Now for the blend, I'm going to set it as 1 so that the base skeleton will follow to this IK 100%. So this should be good. This should be good enough. And in order to test this out, I can move like one of the point of the IK to see if those point after leaving this loop will move. So what I'm going to do is to test out moving some of the tip point of the IK driver right here coming out of this first input. So I can just say select the point. I'm going into the split, maybe connect with the null, and then select this point that I want to move to test. Okay, and move this like upward and see the result. Okay, and if I move this point, you see IK is correctly working. Alright, looks good. Now here is some problem right here. You see that sometimes the legs goes inside, so that's what I'm going to fix inside the solver. But for now, the basic setup for the inverse kinematic seems to work, so that's good. Now I want to check if this works without using feedback iterations. Let me just delete this channel and make it 1 and see if it still works. Now this seems to work. Alright, maybe. How about changing this point? Okay. And if I do this, okay, so this doesn't work. So I guess it was okay creating a for each iterations. Just needed to check. Okay, so let me just paste this back. Oops. Alright, now the inverse kinematic works just fine. Alright. Okay, so the base setup for the inverse kinematics seems fine. Um, I can just go from there to a subsolver now, but let me also create some base setup for targeting the base geometry to this skeleton first, so that I don't have to go that part later on. What I mean is to first create a base geometry for the robot and then target that geometry with this skeleton. And that's not that hard, you just need to use some of the node coming from a KineFX again. Okay, now first of all I'm going to create a body using this polygon. So let's use the extrude, poly extrude, to raise up a little bit. Okay, I might need to reverse to raise up upward. Let's say 0.5, and then maybe instead at some value like 0.2. Doesn't really matter what the value is. Okay, and I'm going to close the back. I'm just gonna make it really simple, kids like robot. Okay, and I am going to use a facet to create a cusp to the edge. So cusp polygon. Okay, now let's also thicken the leg by using a polywire, which can be retrieved from this base skeleton. Okay, this might be too thick. I'm gonna set it as 0.05, maybe a little bit thinner to 0.025, maybe 35. Right. Well, I just say 5. And then I would like to also create some joints for each point positions. So I'm going to create a sphere. Let's set it as polygon with some small size but a bigger than leg. So let's say the radius is 0.1. Okay, and use copy two points to copy this points to this base skeleton points to create a joint like this. Okay, pretty simple, nothing special right here. Let's color this to red. Okay. Now let's merge all these geometry together and use this as a target geometry, which I want to move, which I want to control using the skeleton. Okay. To do that, first I need to create a capture bone from the lines, which is from the skeleton. So there's a node called bone capture lines. I'm gonna use this to use the lines to capture bones. Okay, I'm not really sure what does this do exactly. I'm just following the another side effects documentations. This is the way to do. Okay, and then I am going to use another component called tetra or tet embed right here to create a embedding geometry from the target geometry that I want to use together with this bone. Okay, now looks it's covering all the geometry, so it looks fine. Might be too dense. If you want to make these number of faces a bit more scarce to make the performance better, you can reduce you can raise up this value, min triangle scale, like 0.02. Okay, looks still good. I think 2.5. Let's say 2.5. How about this one? Max that scale. Okay, doesn't seem to change anything, but seems okay. I'm gonna keep as this property. You can test this out. Now finally you can use a node called bone capture by harmonic together with this captured TED embed geometry with a base geometry that you want to change, and then use a bone deform node to first use the one that I have just created as a guide, the geometry that I want to move. And then for the second input, I want to input the base skeleton, which is this one, which doesn't move. Okay, and for the third one, it is going to be the actual moved skeleton. So in this case, a skeleton which has been moved together with the IK chains. Right. So let's test this out by going back to the one of the tip point on the IK target and move this one of the point upward and see if I move this point upward and change the leg based on using the IK chain, and if that also deforms the geometry as well. Okay, so let's throw this up and use the move node. If I raise this up, okay, seems to work. All right, so the base setup seems good. What I just need to do now is to control the position of this this first input, the IK target. Somehow seems like it's walking on top of the ground using a SOP solver. So that is what I'm going to do, and that is going to be the main part of this tutorial. Okay. Alright, so let's do that. Let's do that. I think I have enough informations. Okay, going back to the SOP solver, and then to do that I also need to have some guide geometry which is going to be used as a ground, and to make it a bit more interesting, I'm going to create a rough ground so that not just a flat ground, but making rough, like by using like a mountain node, so that the robot seems like walking on top of like surface on the moon or something, to see some interesting walking animations. Right, that's what I want to achieve. Okay, so let's create that ground, starting from the grid. Let's make the resolutions a bit higher, like 100 by 100, and let's also set the size to big size, like 20 by 20, and then use the mountain node to create some rough surface. The parameter could be anything, but making it too high might be hard for the robot to walk around, so make the height around 2. And then for other parameters, maybe I can reduce the number of octaves, make it a little bit smoother, and maybe this might be okay, might be too rough, might be okay, maybe, but I can just change it later on. So let's just do this. Okay, and I'm going to connect this to a second input for the soft solver as a guide for this cute ones to walk around. Okay, though. Now let's do this. Going into the soft solver, first thing you want to do is to split the geometry into two, one for the space skeleton, one for the IK target. And the first thing I would like to do is to move the base skeleton like randomly, and use that as a guide for the IK skeleton, IK target to set the base positions for each point. And after that, I'm going to control the position of the leg based on the mountain ground, which is this one. Okay, so let's name this. From the first output you get IK target, and from the second output you get skeleton. Right, now first thing I would like to do is to move the skeleton using some random functions or noise functions to move around on top of this surface. Okay, so let's just do that. And as always, my favorite, point wrangle. Point wrangle, right? Let's name this move. I'm gonna connect this mountain from the second input of the soft solver to the second input of this point wrangle as a guide. Okay, now, and after doing all sorts of calculations, I'm going to merge these two together for the next iterations. Okay, so going into the move, first thing I like to do is to create a noise value, like a random value, to move, to just make this robot walk around in any direction. So vector val is equal to using noise. Let's create the random values based on the time attribute, global time attribute, and multiply by some parameters to control the smoothness of the randomness. I'll just name this scale. Okay, and as a result of this value, you'll get a vector value for x, y, and z in between 0 to 1. And in order to make this all directional random value or all directional noise value, I'm going to subtract this by set 0.5, 0.5, and 0.5. Okay, then since the ground is based on the xz plane, I'm going to set the y value for this velocity to 0 for now. Then make it normalize. Okay, now, and say that, consider that I have, at each point I have this velocity value called vel. Well, currently I don't have that value, but by adding the velocity, maybe multiplied by 0.5 to the current velocity, I can iteratively, I can increment the value velocity at each iterations, so that I can create kind of a smooth directional changes where it should move. Okay, making this value smaller makes it more smoother for the directional changes, but I'm gonna keep it as 0.5 for now. Now finally I'm going to normalize the velocity attribute. Okay, so with this I have just created the velocity, which it changes by each iterations and which can be used in order to move this whole points. Now let's do that by changing this current point position with the velocity attribute that I've just created. And since this is normalized, the speed is equal to 1, so let's also multiply this with some custom speed value, which you want to control. And let's set the scale to like 0.2 for now, and for the speed, doesn't have to be really fast, so 0.05 for now. And let's see the effect if the skeleton is really moving. Now going out of the solver and play it. Okay, it doesn't really change. Okay, something is missing, I think. Let me try to enable this one, only enable this one, and okay, I was missing the group for the split. That was the reason. So this should be IK target, and for the point, let's enable this merge again. Going out the geometry. Okay, now it's moving randomly. Now it looks weird because it just looks like it's shifting and the IK target is not moving. Well, that's fine for now. I'm going to copy the position of this base skeleton to this IK target later on. Now, what I want to make sure is that this base skeleton is moving randomly for now, and that looks good. Now the problem right now is that it's moving horizontally okay in XZ direction, but it is not actually following the height of this base ground, like so. It's just going flat, it's just moving flat. So what I want to do is to move this also based on the height of this ground as well. So let's add some functions, additional functions to this move, so that it is also based on the height of this ground roughness or mountains. Okay, so and what I want to do is to keep the height of this point from the tip of this point to the ground same, around the same for all the ground positions, meaning that oops, I wanted to enable this one. If this skeleton is around at these positions, then from the point on the ground to the tip of from the top tip of this skeleton, I want to keep the height same when it was counting from the 0, 0, 0 positions to this height. And currently the height of this skeleton is constant value, which is equal to 1.2. That is because I have added 0.2 right here on the base skeleton node, base skeleton wrangle right here, and the base height of this robot is set as 1. Now maybe I can parameterize this as well. Maybe I should do that so that I can change the height of this robot as well later on. Okay, so robot height to say from 0 to 2 might be too high, 0 to 1.5, and also some offset value for the root point. I'm gonna say height offset, and then set it to from 0 to 1. Okay, for the height offset, I'm gonna keep it to 0.2, and for the robot height, I'm gonna keep it to 1.0. And let's copy the height, paste it right here. Okay. And for the offset, I'm going to copy this value and then go to the base skeleton. Let's parameterize this value right here. Let's name the channel name as height offset. Okay. Now since I have this horizontal offset as well, let's parameterize this as well. Okay, so for that one, I'm going to name as leg offset from range from 0 to 1. And let's set it to 0.4. Copy, paste it right here. Okay, now we want to copy this height again, and then going into the subsolver. Then for the move, I want to get the height value for the tip point, which is going to be the base height for the polygon plus a height offset. So let's calculate that first. Oops. First, a height, global height, and then hello everybody. Okay, and then paste this as well, and let's rename this. What was the name? Height offset, this one. Okay, now let's see if the link is correct. Yeah. Okay, now next thing I would like to do is to look for this point inside this point wrangle. I can do that by, I know that the name of this point is root, so I can retrieve this root point number by using a function called find attrib val for the point class name. The name of the attribute is name, and then this one that I want to search for is the root. Now, as a result, you'll be able to get the point number for this one and apply it for this, stored in this variable. Now from this I can get that position using point function at this root point pt. Okay, and next thing I'd like to do is to let me think. I need to know the height, the current height of this base skeleton on top of this guide geometry, the ground geometry. So I can use intersection functions, I think. So intersect Okay, so I need 1, 2, 3, 4, 5, 6 parameters. First, I need a u and v as an output, and also a intersected point positions. I'm gonna name it as interp. And the guide is coming from the second input. The origin of the intersection is our pos, which is this point right here. Okay, and then I want to cast a ray from this point downward, so I can create a negative value for the y direction, and as a result I can retrieve the intersected point position u and v. Okay, and what I really need is this intersected point position. With this I can, first of all, I can calculate the subtraction between the current point position minus intersected point positions, right? And but actually what I want to do is to move this upward a little bit to keep the distance between the top point of this base skeleton to the bottom point of the ground to be equal to 1.2, in this case a robot height plus height offset. So to do that I need to create some vector, up vector, to create for that. So to move this base skeleton upward. Okay, so to do that I need to first create a 0 robo height plus height offset 0, which goes to y direction, then subtract with this difference vectors between the positions and intersected point positions, which can be named as vector up direction. And if I add this to P, it should raise up the whole skeleton upward. Okay, now down it goes downward. Did it? Well, maybe it's correct, maybe not. Yeah, since the base skeleton, base geometry, base position that I'm looking at is this point, so looks correct. Let me try to move this, walk around and see if the height is changing based on the ground. Okay, so okay, it is moving. It's moving too fast. Cannot see really. Okay, I think it is moving based on the height of the ground. Alright, looks good, I think. And as you can see, I mean, it's just currently I'm just shifting the base skeleton like to X, Y, and Z, and that's it. I mean, I'm not moving the legs yet, so it looks weird enough. Now what I want to do next, this is the final things that I should do, is to control each tip point of legs upward so that it sticks to the ground, and also try to create some walking like animations, maybe using some trigonometry as well, some procedural process to create pseudo walking animations, right, without doing any manual process, by just using coding. Sounds fun. Okay, now the base position of the skeleton looks good, so next thing I would like to do is to copy the base position of the skeleton into a IK target, which is this one. Okay, so I'm going to create another point wrangle and connect to the IK target and use this moved base skeleton as a guide, so that connect the moved skeleton to the second input. And let's name this final, or walking animation. Okay, this is going to be the most important part for today's sessions tutorial, and most long code that I'm going to write for today. All right. And I have realized that I need to process the code for each legs in this case. So it might be better using a primitive wrangle instead of a point wrangle. Okay, so I'm gonna change the run over to primitive. Okay. Right now, let's first access to all the points which is contained inside each primitive using prim points. Like this, and do the for loop to access to each point using a loop. Okay. Now, let me open up the code editor. Okay, now retrieve the point number, and in each array, like this, and then retrieve the point position by accessing to p attribute at each point. Okay, now what else? I also would like to access to a name attribute at each point, which I'm going to use it to change the functions for each point, for top point, middle point, and bottom point. Right? So string name is equal to point 0 name pt. Okay. Now's the time to also retrieve the corresponding point position, which is coming from the second input, right? To get the corresponding point value, you just need to use this name, because actually this IK target is derived from the base skeleton, so you have the exactly same point name attribute at the corresponding positions. So like I did before, I'm going to search for the corresponding point number by using find attrib val from the second input for the point class, and this time the name, I'm going to search for the name attribute with the current name for the search query. Okay. Alright, so from this MPT is the number of the point from the second base skeleton, right? So what I want to get is the point position of this base skeleton for the top, middle, and the bottom for each point, and then copy that point position to the IK target. Okay, so to do that, I also need to retrieve the point position from the base skeleton using the point attribute for the second input, P and PT, right? Okay, now if you just want to copy the direct point positions, then what you can do is to just say set point attrib at pt with npos. like this, but that's not actually what you want to do. But for each point you want to do some different kind of modification for each point for the top, bottom, and top, middle, and bottom. Now for the top part, this is actually a root point, so this can be exactly same as the base skeleton positions, so I can just do the same things like I did right here. For the second, for the middle point, you can kind of do the same things, but what I want to do is to create a long, line like this. Since this is going to be just a guide, this middle point for the IK targets is just going to be a guide in which direction should this leg be bended. So making this line long can be assured to that this leg's always bend outward, not inward. So that's what I want to do for the middle point. I just want to move this point position outward a little bit longer than the original positions right here. Okay, that's what I want to do. And for the most important thing is for the bottom part, the bottom point. This is the point where I want to move like procedurally to make it look like it's walking around, walking on top of the ground, following the ground height, also trying to change the position of the legs by raising up the leg and landing on the ground like a person or like some creatures. So that's the most important part. So for each point you should do a different kind of stuff, so this is where you want to use this name for switching for conditions. So if name matches using B asterisk, else if name matches with M asterisk, or else if name T asterisk. You want to change the modification for each point, right? And for the T, it's pretty simple. We just want to do what I did right here, just copy the point position from the base skeleton. Okay, and let's also do the middle, which is going to be a bit more simple than the bottom. Okay, so to do this, to calculate the middle position, first thing you want to do is to same as what we did last time, but get the center point or average point between the neighbor point of this middle point. So in this case, the middle center point between this point and this point, the bottom point and the top point, then that should be somewhere around here, and create a directional vector goes from this point to the middle point, and from that point you want to move outward, but in order to that's when you want to use the value that you have created previously, which is added as a direction attribute at the point only for the middle, which is this one. And you can use this directional attribute to specifically move the point that you have just retrieved, the average point between this point and this point, to that direction to create a new point, to define the new point position for this middle point. Okay, so I'm going to use that one. So let's do that. First of all, let's retrieve that value directional attribute using point direction pt. I can just use this because I'm running this only if the name is name matches to m something. So, and this direction is applied, this direction attribute is only available when the name is equal to m something. So that works, right here. So that should be good, that should be okay. And now I want to retrieve the center point of the center point positions between this top part and the bottom part. To do that, I'm going to do what I did before, get the neighbor point value, point position, point values using neighbors at pt, and create the average positions. Okay, and then retrieve the first point. Retrieve the second point. Retrieve the point position. Retrieve the second point position and get the average point position by adding those 2 points together, multiply by 0.5. Okay, let me check if the position seems to be at the same correct point by adding the point temporarily. Okay, I don't see anything. I think I need to enable this one. No, I don't see anything. Okay, let me just apply, accept, and go out of this soft loop. Go back again. Now I see a point. Looks correct. Now what I want to do is to move this point outward using the direction attribute that I have created. I mean retrieved from the point attribute. So, which is this one. So, and the length of this direction is equal to 1, so that's pretty long enough in this case. The size of this robot is not that big. So after creating average positions, I can just say average position plus equal direction. If you want to make sure, you can multiply by some greater value like 2. Then check that point positions. Now looks far enough. Now instead of adding this point as a new point, I am going to set this middle point position with using set point attrib at pt, like this. Now looks pretty long, looks pretty weird, but it's just a guide. It's just the IK guide, so it doesn't really matter. I'm just making it long enough so that this will be used as a bending directional guide. If you think it's too long, I mean, doesn't really matter, but you can change its value to keep it a bit more proportional. It doesn't really matter. Okay, now good. That's good for the middle point, I think. Now's the time to control the bottom point, which is the most complex. I mean, which is going to be the most important part of this walking simulations, walking animations. Let me save this, then go back to the working animation primitive wrangle. Okay, now let's do this. Give up some space. Now, first of all, I need to define like how many frames you want to use for one step, like from raising up the leg to the landing. Okay, so that's one of the parameters I want to have, I think. So let's promote that as a parameter. Int total move count. I'm gonna name it as total move count, and use chi total move count, actually used as a frame value, step frame value. And let's also promote this. And by testing out by myself, seems like with this kind of size, I mean, it depends on the size which value should be better, but for my size of choice, 10 was good, so I'm just gonna leave it as 10 for now. If you make it like bigger value, like 20, the movement of one step becomes really slow. If you make the value like low value, like 5, one step will be really fast, so it's like walking really fast. The gesture of the walking will become really fast. So it depends on your needs, I guess. Right. Alright, so, and addition to that, I need some additional parameter for the bottom point. I mean additional attribute for the point, bottom point, in order to determine in which frame is that point is on. I mean, and also some statement value if the point is currently moving or not moving. Currently moving is that the leg is in the duration in between raising up the legs to landing the legs, and some of the legs might not be moving at some frames, might be staying at the same positions. So you might also want to have that kind of state if the leg is moving or not, and also if the leg is moving, then in what frame count is the point is in. Is it on the last point, or is it on the last frame, or is it on the first frame, or so on, or it's in the middle frame, to determine the height and the position of the legs to create an animation, right? So that's kind of a value that I want to create. So for the frame count for each point, I am going to retrieve an attribute called move count from a point. Now initially I didn't really create any attribute called move count, so doing this just give you a value equal to 0, and create a empty attribute called move count to that point as an integer. Now it might be too hacky, but this works. Okay. Now next I need to check if the point is moving or not, so I'm gonna use point group to determine if the point is moving or not. So I'm going to access to a point group called isMoving, and for this one as well, I didn't set any group previously whether the point moves or not, but by saying in point group with specific name like moving, it just creates a new group if it doesn't exist to that point. So I'll just do it this way. And initially the value, if there's no group named moving, then the initial value will be 0. So that's also fine. 0 means it's not moving in this case. Okay, so I have just created a is moving variable using a net point group to check if the current bottom point is moving or not. If is moving is equal to 0, which means the point is not moving, then I want to do something, then else I want to do something else. Okay. Alright. So easier stuff is to starting from when the point is not moving. Okay. So what I'm going to do here is what I'm going to do when the leg is not moving is to check when to move the point, when to move the leg. Okay. So say that think that maybe it's better that I draw it on sketch. So currently I have this, if I look at from the sections, I have this top point and the bottom point and the middle point. Like this. Okay. And currently by moving the base skeleton, this top root point is moving somewhere. Like this, okay? And corresponding to this point, these middle point also moves a little bit. But the bottom point tries to keep its position at that point, like this. So what would happen is that if the base skeleton moves to a same direction, then you start to have a really distorted leg like this. Seems like it's going to like lay down. So in order to avoid this, at some point you have to move this leg so that it will come to somewhere around here to keep the shape of the leg stable at this point. This is where you want to animate this arc. This arc movement of the leg is where you want to animate, right? Makes sense. And in order to define when to move that leg, you want to check, what you want to check is the distance between this point to some of the guide point, like the middle point. Say this is the ground and this is the center point of the base skeleton, and if you're looking at this point, and check the distance between the legs and the center point. Okay, and if distance is bigger than some threshold, then you want to start moving this leg to the center, going into the center to stable positions. So that's what I want to do here. So when the leg is not moving, I want to make a condition by calculating the distance between the point of the leg to the center of the base skeleton. And if the distance is far enough, we're using some threshold, then I want to set that point, set that foot point to start moving for the next frame. Right. So what I need to do is to first calculate the distance, right? And the distance that I want to calculate is maybe not the center, but since currently, say this was the base skeleton, right? And for the base skeleton, I'm just moving the whole geometry like this, right? And for the target, IK target, what I was moving is on those top point. Wait, I'm opening the cap to right here, directly to here, and this one to here. So as a result, you are having a geometry which looks like this, right? But I'm not moving the bottom point. And the middle point is based on the position for the tip point, top point, and the bottom point. So currently I can just ignore this for now. So for the bottom point, what I can do is to calculate the distance between the original base skeleton foot plane to the corresponding tip point, which doesn't move, which is not moving currently. Same for this one. So this could be the distance that I want to calculate. And if those distance is too far, then you can start moving this foot point. Makes sense? Hopefully. Alright, so let's do that. So calculate the distance between the current point positions to a guide positions from the base skeleton. Then let's also create the threshold. Alright, so I can create some parameters for this one, and to make it a bit more organic, maybe I can add some random values as well. So rand with some positional value multiplied by same thresh, I guess. Or I can just say thresh multiplied by 1 plus rand. Okay. So the rand will create a value in between 0 to 1. Alright. Now, apply, promote, and for the threshold, so more threshold you have, longer it takes to start moving the foot point. If you have less threshold values, meaning that you don't, the robot starts to move the legs as soon as possible. Now for now I'm going to keep it by 0.3. We can change this later on to see the differences. And some parameter, if you make it too big, might not work well. Okay, now that I have just made a threshold, let's compare the distance between the threshold. If the distance is more than this threshold value, then it's time to move the point. So what I want to do is to set a moving group first. So set point group to that point, named as moving to 1. Okay, and start counting the moving count attribute, which is this one. So reset the set move count to 0 since you have just started moving. So move count PT to 0. What else? In order to calculate the arc-like trail from the raised up point positions to the landing point position, I might need to remember, or I need to recode where this point started moving. So I'm going to recode the current point position where it started moving, which is this point positions, as an attribute, so that I can use it later on while it's moving. So set point attrib, I'm gonna name it source. Okay, and PT position. Okay. Now, it's also, since we are working on top of the rough ground, we also want to change the point position in a Y direction, right? So let's also do that. I can either use intersection, or I'm just gonna make it simple to just use minimum position. Might not create a better result, might not give you a better result compared to intersections, but it's easier. So vector, let's just name this ground positions equal to min pos. Now I didn't connect any ground informations to this wrangle, so okay, this is the ground. I'm gonna connect this to the third input of this primitive wrangle and access to this using this min pos with the current point positions, or maybe or pos in this case. This is the foot point positions. Okay. Okay, and then what I want to retrieve is just the Y value of this ground positions and update it to the position that I have retrieved from the base skeleton. So n pos y equal to g pos y. Right. Okay, now I also want to set as an initial attribute, initial value, since this is the starting point, the starting frame when the foot point is moving. I kind of need to define in which direction should this foot move to, right? So that's kind of important, right? Now, what I could think of is, well, think that this time I'm looking from the top, okay, and the base skeleton's moving randomly, right? And each point, and when at some point when the base skeleton comes right here, and one of the legs might want to start moving, okay, and when that condition met, and say the legs is something like this, and the direction where this tip point of this foot want to move is, I guess, the same direction as the base of this skeleton goes. So currently the base skeleton is moving towards this direction. So for this point, maybe I can start moving the legs to the same direction as the body. And that could, my guess is that that could make the movement a bit more natural, rather than setting randomly, setting the direction randomly. Okay, so to do that, I need to retrieve the body movement direction, which is coming from the second input, which is this one. And if I look at it, I can retrieve that information from this velocity vector attribute at each point, which is actually used to move the base geometry, right? So simple that vector. I'm gonna name the retrieved directional value as move direction, and access to the second input, name vel at npt, and this is the direction where I want to move the foot to. So now let's create another attribute called target, and let's set it as a final destination. Okay, so pt, and for the final destinations, what I want to do is to first give a current point positions, then calculate the differences between the base skeleton and the current point positions, which is npos minus position, so that at least it's trying to move to the original base skeleton positions. Then use the moving direction that I have just retrieved to go further with some moving distance, and that distance could be, say, same as the one that I have created right here, threshold. Alright, I think this makes sense, doesn't it? Now I need to close the parentheses. Okay, so this is going to be the target point position. This is the source point positions. Now that I have two informations, source and target, in between them I can use the move count attribute, which goes from 0 to maximum total count, which is defined here, in this case equal to 10, and to create a arc-like movement, doesn't it? Alright, I think that makes sense, hopefully. So this is where I have set the initial movement conditions. Now this else condition is where I actually want to write the code in order to define the animation, define the foot movement. And there I can use something like a combination between the source and target, plus in order to create the arc-like movement I can probably use like assign functions to create an arc-like trail. Sounds fun. Okay, now so I have move count right here, and first thing I like to do is to increment the move count when it's moving, when the foot is moving. Okay, and update the move count attribute at current point. This. Now I want to create the value, first create a value from this move count, convert it into a value from 0 to 1. So that should be easy. I'm gonna name this move f equal to move count divided by a float value of total move count. Now that's not actually a value in between 0 to 1, it's actually a value between 0 to some 0.999 something, which that's okay. When it becomes 1, that's where this should be activated, or I mean, yeah, the movement should stop. Okay. So right, so the first thing I would like to calculate is the height of the leg using this move F value plus a some parameter that I can set. So float F using sine function together with the pi multiplied by move F, so that I can create a positive arc, and in order to multiply this with some parameters like height to control how much the leg should be raised up. Okay, I gotta be careful. So let's set the height to some small value like 0.3. Okay. Now that I have just created a height, let's retrieve the target positions and source positions from the point, which I have created right here when the point started moving. So vector source is coming from the source pt, vector target coming from point attribute target pt. Okay, I'm getting tired. Now I'm gonna create a attribute called, variable called tpos, which is going to be the final point positions. And first I'm going to copy from the current point positions, right? Now I'm going to create the linear lerp between the source and target using a move F. So maybe I didn't need to copy these positions, but use a lerp. Okay, so I think this can be used with the vector, right? So from the source to target with the move F, I can create interpolated positions between source and target together with the move F, which is in between 0 to 1. Now let's also calculate the height, since we are moving on top of the rough ground, mountain ground. So let's just do the same things that I did here. Calculate the minimum positions. Okay, like this. And then this time what I'm going to modify is this tpos y, and currently this is just a linear change, so the height is not changing. But what I want to do is to first use this h variable, which I've created with using sine value, which is going to create an arc-like shape. So h, right? But probably you might also want to let's see, if I'm thinking if I should relate the height using the source and target, or I should just use the ground position that I have just retrieved. Either way might because if I'm not using the height retrieved from the source and target, then what I did here doesn't really make any sense. Well, I'm just gonna ignore that then. Okay, so if I write like this, these things that I write here doesn't really make any sense, I think. If you want to use those values instead of writing like this, what you can do is to say plus equal h, and that's it. And without using the minimum positions. But I'm thinking, since we are moving the legs like in real time, and the body of the body position is changing on every frame, so the height of the ground is changing in real time, so keeping the height real time might be a good idea rather than using the old recorded values, which might be too old to look for. So we're just gonna go like this way. Okay. Okay, looks fine. Then I'm going to update the current point positions using set point attrib ptt pos, right? And there is a moment when the move count reaches to a total move count. That's when you want to stop moving. So that's when you want to set the point group moving to 0. So set point group 0, moving pt to 0, and then reset the move count to 0 as well, which might not be necessary because I'm doing it right here, but just in case. Alright, that was long and I got an error somewhere. Let me see. Invalid source. Okay, doesn't really, okay. I'm missing semicolon somewhere. 35, 24. 35, line 35. This one. Oh yeah, weird. What's this? Okay, I am okay. What's wrong? Let me just say apply and accept, and okay, something weird is happening. What is this? Vector. Seems like I'm having a copy of same code. I'm not sure why. Right. Okay. Now, what else I need to do? I think I have done all the things that I need for this code, and hopefully, finger crossed, it works. If it works. Now, check out by going out of the solver, and also let's show up the ground and see if the legs is moving corresponding to the ground. Okay, it does seems like moving. Now the IK is not working because I haven't activated yet, but overall looks okay. Now's the time to see the final result by activating this one, this loop, and then showing up the ground. Okay, well, the leg is moving somehow weirdly. Yeah, it's not correct. It is wrong. Something is wrong. Let me just show. Okay, yeah, it's obviously something is wrong. This does not correspond to this. Okay, yeah, something is wrong. Let me just check. Something must be wrong somewhere in the code right here. Okay, let me open up the code again. First of all, let me check some parameters if I have everything that I need. So I have threshold, total move count, height, and let's also check if I have necessary informations like move count right here, and moving group, yeah. And let's also check if I have unnecessary informations. So I have source, target. These looks good. These looks correct. Okay. Now I think somewhere around B, name equal to B is wrong. So let me check. So it's first it's checking the moving, whether it's moving, and if it's not moving, then first calculate the distance between the position to the base skeleton distance. Then I'm calculating the threshold right here, and as a result, I should be able to get more than 0.3 values right here. And if the distance is larger than threshold, then hello everybody. Will we see your books in English? Well, for the books that I wrote in BNN, I'm not sure if it's going to be translated into English. It's really up to the publisher. So hopefully it does, but I'm not sure really when. Okay, and the move count. Checking the move count. This should be also good. Min pos. Yeah, this one must be okay as well. And well, these doesn't really matter, I guess. And the target point positioned. Let me go back to somewhere around here and see what seems to be wrong. Okay, at some point it's some point this point is moving too fast upward for some reasons. Now let me check by adding this target point and see if this calculation is correct. Okay. Add point. Oh. Okay. Now this seems to create a point at the weird positions. Am I getting... First of all, am I getting the right name? That's the question. Going into the NNN. Okay, which I don't see it right now. But let me just leave the solver, going up again, and okay, I should look at the primitive. Right now, okay, some of the name is missing. 1, 2, 3, 4, 5, 6. Is that okay? Well, but yeah, I think that's okay because I have 6 legs, so that should be fine. Let me just apply it. Okay, let me look back at the code. Let me cheat by looking at the code that I wrote previously. Maybe something is wrong somewhere. Not really sure. So I have this move count, and I'm updating the move count, and the move ifs. This should be correct. And multiplying by height. Yeah, that's should be okay. Source target. Source target. Am I missing the spell? Nope, looks correct. Okay, and using lerp from source to target. I think that's also okay. And oh, right. Why am I adding? It should be equal. I guess that's the reason. Okay. Small mistake. Stupid mistake. Hello, I'm from Japan. Okay, now let me check again. Going into a loop, going out of the loop, check out the ground. If I play it, alright, looks organic. What's those points? I think I'm adding points, which is unnecessary. I think I did that somewhere for the debug. Where did I do that? Where did I do that? This one. Yeah, I don't need this one. Okay, but overall looks good. Now it's the time to show up the robot, which is already targeted at the bone. Yeah, looks like it's moving. Now I want to show the ground as well, so let's merge those two geometry together. One is the robot, one is the ground. Let's color this, let's color the ground, right? So I am going to color this some interesting color, but after all it's just a constant color. Just color this blue. Okay, and if I play this, hopefully the robot seems like walking on top of the rough ground. Alrighty. Now everything is set up, it's time to change the parameters to see how these changes the parameter effects. But some of the parameter isn't being promoted yet, so let me do that first. First of all, those 3 values, maybe I can parameterize this to control. It's this one. For this one, I can control the scale, which was the smoothness of the movement and the speed. Yeah, I can just bring everything. Alright, so I'm gonna open up the controller, edit parameter interface, uncheck for a bit linking parameter, then going back to the subsolver and drag and drop. First scale. Move smoothness or movement smoothness, and then the speed. Maybe I should say moving smoothness. Okay, apply. Now go to this one, then total move count, threshold, and height. So the height is the leg raise height, and the threshold is distance when to start moving the leg, so leg threshold. And the total move count is the leg, like how many counts you want to use to move the leg, so leg frame count, leg frame count. Okay, everything is promoted. It's time to see the effect by changing those parameters. First of all, let's say in order to change the shape, I can, if I want to change the number of legs, I can go to the legs numbers. Like if I want to change the leg number to 8, change 8. If I want to change the radius, I can change the radius. And then the root height, like 1.2, make it higher. And leg offset to make the wider. Now it looks like an alien robot. Now after doing some shape changement before the skeleton, before using the skeleton, you need to go back to the skeleton to click this dash input to update the skeleton. That's a bit of manual like process, but kind of need to do that. Now after this, you can just use any kind of parameters. Now let me just first see if this still works. Yep, seemed to work. Cute. That is cute. Let's set the range to 1000. And then let's try to change some of the parameters, which is not for the shape but for the movement, like leg frame count. Now currently it's set to 10, but if I set to 5, then let's see how it goes. You see that the movement of the leg becomes really fast. If I make it bigger value, like 20, becomes slower. Like it's like walking on the moon or something. It's like jumping. Maybe making too much time. In order to avoid it looks like jumping, maybe I should also control if I want to keep the leg frame count. I think I should reduce the moving speed or set the threshold smaller, I guess. If I set it to 0.15, maybe not. Maybe I should just set the speed slower, like 2.5. Okay, that kind of makes sense. It's really like moving on top of the moon face. Maybe too slow. I'll just give it back to 0.5 and 10. And if I set the leg threshold to bigger value, you start to see the leg what keeps at its position for some distance. And sometimes it gives you kind of a jumping like movement. For now it looks okay. 4.4 still okay, but if I set it to 0.1, now it looks like dancing. Yeah, I'm gonna keep it to 0.4. Now if for the leg raise height, you can raise up, you can control how much you should raise up the legs. If I raise this up, it looks like drumming on the ground. If you make it too small, it's like ninja-like walking. Let's give it to 0.3 for natural looking movement. Okay, so and you can also control the speed. Oops, too fast. Whoops. Once it's leave the ground, since I'm using the minimum positions, it just goes away. Okay, and if I increase the moving smoothness, it starts to move really randomly. If I make it really low, the smoothness becomes bigger. So I guess the meaning is other side. I think I should say moving randomness. Oh well. Now it jumped to somewhere. Once it's leave the ground, maybe I should set the ground a bit bigger, to 30 or something. Okay, okie dokie. So that's pretty much it. I hope you find something new here. I'm not sure. I mean, the way I made this procedural animation is pretty brute force, using a lot of coding, so might not be an effective way to create this kind of things. Maybe there are much more effective way to do this. But I just wanted to try this new feature called KineFX, and I had a lot of fun playing it out with it. And I'm not really sure what to do with this robot, so I hope somebody who find this interesting would use this for some interesting purposes. Now I am going to upload the file, the HIP file, to the GitHub repository, which can be downloaded from the video description page of this video, this YouTube streaming. I am also going to left the recording. So hopefully, I mean, if you want to rewatch, you can always do that. although it's really long, just to remind you. Okay, so it's a good time to finish this lecture for this week. Took like 2.5 hours, so very thankful for who have left here to watch. Thank you very much. If you guys don't have any questions, then I would like to end the tutorial here. Okay, I have one question, I think. How difficult would it be to control the front 2 legs so that you may raise them in an art directable IK handle fashion, but also have them behave with the rest? I guess have slider between. You may raise them in an art directable IK. Well, for example, if you want to control like 2 of those legs in a more controllable fashions, I guess what you can do is to create a group for those 2 which you want to control. Then for those points, for those legs, you can specifically get that point position for the bottom point of those 2 foot that you want to control inside the subsolver. Maybe you might need to add another conditions other than these ones. So within this one, maybe you have another if conditions inside this conditions to define which ones you want to control, and start writing some additional control you want to apply for that legs. Maybe that you can do. Maybe that's what you can do. Right. How do you remember the code? No, I don't remember the code. I mean, I am just cheating what I have written before, which is right here. Yeah, surprise. So I'm just looking at the sample code shown on the other display. I cannot just write it from scratch. I cannot just remember all those codes, long codes in my mind. Right. So I have previously made the sample code myself. Then I'm just following that by explaining how I did it. I mean, what I did while I writing. That's how I write. It is hard to remember, I think. I mean, I could think of a method that I have used, but like following the little steps detail is not that easy to do, so yeah, I don't have a mastermind, so I hope I did, but unfortunately not. Okie dokie. So if no questions, I would like to end here. Thank you very much for watching, and thank you all for the comment as well. And yeah, I kind of enjoyed this one, and hopefully you could come back next week for other type of tutorial I come up with. Currently I don't have any image what to do, but hopefully there's going to be something interesting coming up. Alright. Okay, so wait for the files that I'm going to upload, you can go back to the video description page to download it and for you to look back. Okay. Thank you very much and good night, everybody.